Hello, let's review a solution to our field optimization test problem. To change the speed that you're viewing the video, feel free to use the controls at the bottom right of your screen. We're going to start off by reviewing inputs in our geometry and meshing section, left for you in the starter file. Starting off, we have our imported inner and outer CAD bodies. In this example, we are going to be infilling our inner section with a field optimized lattice, while the outer body remains solid. In order to tie these two together, we need to use a tie constraint further down in our workflow. But in this section, we are creating our faces to use in that constraint. For our inner body, we have our inner faces selected, and then for our outer body, we then have our corresponding outer faces. Our final face list here is then going to be used for our constrained faces that we are going to use to apply our displacement constraint also further down in the workflow. Next in this section, we're going to then take our CAD bodies and turn them into implicit and meshes. We do this by using our implicit body from CAD body block and then our mesh from CAD body block as well. We then repeat this same exact process for our outer body that we used for our inner body. Once we have completed this, we can then do a final Boolean union with our inner and outer bodies to make one solid wrench. After this, we can then move on to our meshing section. In order to run our optimization, we need to have an FE volume mesh of each region. To make this mesh, we are going to use a remesh surface block, then a volume mesh, and then an FE volume mesh block to create both our inner region and our outer region. We use the exact same meshing pipeline for each of these with a consistent mesh edge length used in this variable here of 1 millimeter. Once we have our FE volume meshes defined, we can then go about creating our parametric FE model. Starting off in our model, we're going to be using our predefined material located again in the starter file, and then we're going to go about creating a parametric lattice component for our inner body. To do this, we then use our inner FE mesh as the input with our material, our unit cell, boundary behavior, cell size, and then our thicknesses listed here below. When we view it on our screen, we then see the corresponding initial thickness inside of our lattice component. Next, to create the component then for our solid outer body, we use FE solid component. In this block, all we need is a solid mesh and a material, and then we have our solid outer component. To tie these two components together, we then need to use a tie constraint. We then use FE face boundary blocks for our independent and dependent regions, and then use our inner tie faces and our outer tie faces to define each of these. If we view this tie constraint now, we can see the selected nodes in between our inner and outer region connecting both of our components. Finally, we can create our finished parametric FE model with our inner lattice component, our outer solid component, and our tie constraint. The next step in creating our field optimization block is then going to be defining our optimization objective. We are going to be using a structural compliance response, and to do this, we are going to define a force and then a displacement restraint. To apply our force, we're going to use our force boundary included in the original file, and then we are going to use a vector in the negative x direction. To apply our displacement restraint, we're then going to use an FE face boundary using our constrained faces, and then applying a 0 in all of these directions, so we have 0 degrees of freedom at any of these points. Finally, we use these two as load cases in our structural compliance response block, and we have now completed our optimization objective. Next, we are going to go about defining our constraint. For this example, we're just going to be using a volume constraint, but we need to specify the region that we are constraining our volume. To do this, we use FE region by body with our inner body, and then a volume fraction response that it is inside of. For our value, then we specify less than 0.3 of our original volume. In our next section, we can then build our field optimization block. Inside of this block, we then will input our parametric FE model, our optimization objective that we choose to minimize, and then our constraint. The rest of our values we can leave as default or change at will. Once our response runs, we can then view our field optimization on our screen. Here we can see the varying thickness values of our lattice to support our applied force with our displacement restraint here. This is our implicit view, but we can also view each component and the property and state fields that accompany it as well. Finally, to post-process our result, we are going to use the property chips located inside of our field optimization, inside of then our optimized model, our parametric FE components, our body list, and then our list elements. We're going to drag each of these into the notebook, so then we have our inner body final and our outer body final. Now to combine these two and have a finished result, we'll do a simple Boolean union with a 1 millimeter blend radius, and then a Boolean intersect with our original full wrench design region. So we now have a flush field optimized design. Feel free to download the file supplied below for a finished copy of what we just reviewed.